working. Okay? So I know a lot of you teenagers think that you work really hard and that your schedule is very hectic, but you're not working every second, every hour, every day for your entire life. You get to sleep sometimes, right? Not your immune system. Even when you're snoring away or having a good nap, your immune system is working hard and always on guard. So I hope I've impressed you with how hard that immune system works throughout your lifetime. Yes, ma'am. The question is, when does the immune system actually kick in and how do you tell? That's not really well defined yet, but we know it's actually pretty early. It's not as easy to tell for the immune system as it is for something like the heart, because when you look at the first ultrasound, you can see that little tiny heart. It's harder to see immune cells at work. So we know that it's fairly early. I can't give you an exact time. There are some pediatric immunologists who do study that. So we're learning more about that all the time, but it is early within the development of the fetus. Okay? All right, let's keep moving along here. We've got a ways to go. Next question is what? Who? Okay, you guys are good. Okay, so who has an immune system? We all have an immune system, okay? Every one of us has an immune system. And for the most part, our immune systems are very, very similar. Now, there's no doubt that during our lifetime, we have a lot of environmental influences that can kind of change our immune systems and change the way that we react to the outside world. So the environment is important, but we're all born with similar types of immune systems. Now, the other thing that's important to realize is that all vertebrates have immune systems, and many of them are very much like ours. There are whole floors of laboratories here that can study the immune system in mice, for example. Now, thankfully, we're not identical to mice. There are some differences. But there are animals who have many similar things about their immune system that humans have. And that's a little bit humbling. And even invertebrates, animals that don't have backbones and have been on the planet for a long, long time, they have immune systems too, although there are some fundamental differences between the immune systems of humans and the immune systems of some of the animals, and especially animals we're less closely related with, maybe fish and, say, reptiles. There are some significant differences. Okay, so what is this? Oh, somebody is really good. This is O'Hare, the Chicago International Airport. So why do I have a picture of this? If you think about an international airport, it is just mind-boggling. You have thousands of people who arrive every day by bus, by car, by plane, by taxi cab, by limo, and all of these people arrive at the airport and then they might check their baggage. They go through security, right? Everybody's checked at security. And then they might go get something to eat. They go to their terminal. Then they hear their flight has been delayed and it's at another terminal. They go somewhere else. And then they take off maybe a short distance or far away. And then all the planes come in. If there's a bad storm, they change the whole schedule around. They adapt and something else happens. The complexity of an international airport is so impressive to me. But let me tell you, this airport has nothing compared to the immune system. The immune system is mind-bogglingly, is that a word? Mind-bogglingly? It is now, more complex than Chicago O'Hare International Airport, okay? It is a very complex process. So what I get to do now is in the next 10 or 15 minutes summarize key aspects of the immune system so that when we meet Elizabeth, we'll be able to think about important parts of the immune system that we've just learned about. Okay, so what are some of the key players in the immune system? Well, there are what we call sentinel cells in tissues. So as we talked about before, if you have a cut in your skin, there are cells of the immune system there waiting, and their purpose there is to identify something in general and to wave that sign. Anybody see Lost in Space in the early 60s? I was, of course, way too young for that. But, you know, there was danger, danger, the robot always said, the earlier R2-D2. And so some of these sentinel cells say, here's a foreign substance, this is dangerous, we need to act. Okay, they're sentinel cells, they're up front, they're like the security guards. But they do a lot more than what we might think. Circulating cells, examples might be neutrophils, monocytes, eosinophils, and lymphocytes. And we're going to cover a number of these in more detail in just a minute. And then tissue cells. Well, you wouldn't think that actual structural tissues in the body would be involved in the immune system, but in fact they are. There are cells that are just staying in place and they're part of the body that are nevertheless involved in immune responses. So when I say that the immune system is almost everywhere in the body, I truly mean it, with all different processes going on. And so it's very, very complex. But let's take a little closer look at some of these cells. So stem cells are the baby cells. And the stem cells remember that picture that had the bone marrow? Okay, that's where the stem cells come from. So the stem cells have a choice. They can become myeloid cells of the lineage myeloid cells and mature into any one of these cells following the arrows. Okay? Or they might decide to mature into the lymphoid line, and the lymphoid cells become T lymphocytes, so-called because those cells mature in, remember that thymus I talked about underneath the breastbone on the lymphatic system? Picture there was a blob right under the breastbone there. The thymus is where T lymphocytes mature. And if you want to use sort of a military analogy, the T lymphocytes and the lymphocytes in general are kind of like generals in the military. They make executive decisions about what to do. The B cells generally mature in the bone marrow, but they also have much more maturity within the tissues and the lymph nodes. I showed you some of those pictures of the lymph nodes. The B cells are very active in the lymph nodes, and that's where T and B cells talk to each other. We'll talk about that a little bit more. NK cells, natural killer cells. I'm not really going to address those very much tonight. We used to think that natural killer cells were predominantly part of what we call the innate system. The innate system is what acts first, and we're about to talk about that. But it turns out that in recent years we've learned that the natural killer cells, which will kill you unless you convince them not to, okay, so they're automatic killers unless you instruct them not to, give them the right signals. They actually are very important with maybe even a little bit of memory. So the cells are quite complex, but we're going to take a little bit closer of a look at some of these. But we're going to look at it specifically in the context of infection, okay? Because we've talked about programmed cell death and cancer. We've talked about cleaning up wounds and all sorts of things. But to sort of give an example, we'll talk about infection specifically, okay? Different types of infection. Let's think about viruses, bacteria, fungi, worms, parasitic protozoa. These are just examples of different kinds of organisms that can be an external threat to us that might want to eat us or devour us or live in us or in some other way wreak havoc with our bodies. And so the immune system responds in a couple of ways. Innate immunity is in general, kind of the early response, where you've got those sentinel cells right up front that recognize that there's an invader, okay, and they respond. The adaptive or acquired immunity, the adaptive immunity is the subsequent response. And what's really neat about the adaptive immunity is that it responds very specifically to that organism, okay? So, one of the things that I wanted to mention before looking just a little bit more closely at that is the general time frame. The innate immune system takes place in about, within immediately to about 4 hours, where that initial recognition occurs. Danger, danger, something's going on, we need to react to this, okay? Then, for the next 4 to 96 hours or so, there are some other signaling going on, and these cells signal the lymphocytes, and they give them the general signals about what is happening, and they present evidence of this foreign invader, and then those lymphocytes make decisions about how to respond. But it can actually be days before you get the really specific response exactly for that particular organism, okay? So you get a general response to begin with, and then a more specific one later on. So let's take a brief look at some of the ways that we have of battling infectious organisms. Well, one might be a mechanical or physical barrier. What's one physical barrier we've mentioned already? The skin. Very good. But there are other barriers as well. Let's say you happen to swallow a nasty bug that wants to give you a gastroenteritis. Well, I guess norovirus is the popular one right now, right? A lot of people are getting infections and nausea, vomiting, diarrhea with this particular kind of bug. So if you think of what it has to survive to do its duty, it's a lot. Even if it manages to get past what's going on in the throat and the saliva it has to mix with, and then even if you swallow it and it gets in the stomach, your stomach is churning things all around. You swallow. How much mucus do you think you make and swallow a day? A liter. At least a liter, maybe more than that. Sometimes 2 liters, depending on what's happening. So you make a lot of mucus and saliva, and you know that when you eat things, you produce saliva, right? And then you swallow it. So this poor bug has to compete with all that mucus and saliva. It's being churned around. I mean, it must be kind of an uncomfortable ride going down there. So there are chemical barriers as well, which would be acid. The stomach has a lot of major acid in it, and a lot of bugs can't even survive that. Okay, so that's another challenge that a bug has to overcome. Microbiological competition. I mentioned that you guys really are, just to quote one of my colleagues, Homer Boucher, you are really just munibuses for bacteria and various organisms, because we are loaded in the gut, especially with billions and billions of bacteria. And any infectious type of organism has to compete with all that. So you can imagine how difficult it would be. You get down there and all of a sudden you and a billion of your closest friends have to, you have to compete with all of them to be able to try and actually infect your host. The complement system, very briefly, is a part of the immune system that kind of tags the foreigner, okay? So I would put like a red tag on that particular bug, and that gives a signal to other parts of the immune system to kill it, deal with it. Okay? And then there's another part of the immune system we're still learning so much about, toll-like receptors. Toll-like receptors also are part of the innate immune system at the front line, and they just recognize patterns. So you know, in World War II, if you were an American and you had an American uniform on, if you saw someone else wearing an American uniform, you would assume what? You wouldn't want to shoot that person, right? You would want to say, you're okay. I'm going to move on. That's an example of tolerance. I recognize you, you're okay, I'm going to move on. But if you were an American soldier and you came face to face with someone wearing a Nazi uniform, your alarms would go up and you would say, I'm at risk here, I might die, I've got to take care of this, I've got to handle this. So I wouldn't know, or that soldier wouldn't know the other soldier's name. He wouldn't know where he was from. He wouldn't know his ancestry. So he wouldn't know the details about him, but he would know that he was wearing the wrong kind of uniform, and I need to get help here. And that's an example, it's really simplified, of what toll-like receptors do. So you can see there are all these different ways, and this is just some of them, that the innate immune system up front deals with unwanted bacteria and other types of organisms. One more thing, phagocytes. Phagocytosis, your next vocabulary word. Phagocytosis comes from the roots to devour, sell, and process of, okay? So if I'm a phagocyte, and I showed you some of those cells on that cell line before on the right-hand side, like neutrophils and macrophages, they're examples of phagocytes. And if I'm a phagocyte, I come in contact with you and I don't like your looks, what do? I eat you, okay? It's as simple as that. And I eat you, and then I process you. I chop you up into little bits. I process you, put you down the assembly line, and then my plan is going to be to present a little piece of you along with a self-recognition to maybe a lymphocyte to say, this is me, don't kill me, and this is a piece of this little organism that I ate. What do you want me to do about it? Okay, so that's how some of that communication occurs. So phagocytosis is for ingesting things that the immune system doesn't want to have. And I've got some cool pictures here for you. Here, this one is actually from a mouse. And you can see that this macrophage, one of those cells that we were showing, is actually putting out these, they're almost like hands. It's sensing its environment. If it finds something it doesn't like, it's going to bring it in and it's going to ingest it, okay? So it's just to show you, it's not just a little round blob like you might see in a textbook. These are very active cells. And here's another one that's really good. This one is, remember we talked about anthrax at the beginning? This is a neutrophil here in yellow that is starting to consume anthrax. Okay, you see that? So this is one of the ways that we can address anthrax, but nevertheless, even though we've got a good immune system, anthrax can kill a lot of people. So these cells are very active, and that term is phagocytosis. Okay, and I have something special for you tonight, and we'll see if this video will come on, which it should. And this is an example from David Rogers, who actually filmed this quite a long time ago now. He's from Vanderbilt. It's on YouTube. It's much better than any video game. You can go in and watch neutrophils consuming bacteria, okay? And here's an example of that. So there's the neutrophil. It looks like this little cluster of bacteria is running for its life. It's running, or it's actually not running, but it kind of looks like that. So the neutrophil is sensing it, because the bacteria is sending out almost a scent that it detects, and then it engulfs it. Okay, yay, victory. Okay. So that's an example of phagocytosis in action. Pretty cool, huh? Okay, and beyond all of that, you have something else that is very important in the process of these initial stages of immunity, and that is these cilia. Cilia are hair-like projections, in this case from an electron micrograph, of the trachea, which is the large part of the windpipe. And these hair-like projections move constantly, like this. And so if you inhale particles, or you have particles that you don't want there, these cilia continuously point the way to the exit for all of these particles, okay? So this way, you want to come out this way. So these cilia are very important to help move things to the exit door rather than letting them get deeper into the body. I hope none of you smoke, and the reason why is because what? Correct. If you smoke, you destroy your cilia. So you know, after you hear for years, people who smoke, they hack and they start getting all this phlegm, and you can kind of hear them coughing up. Part of that is because they can't manage that mucus and phlegm anymore because they've destroyed the cilia, okay? So for several reasons, the cilia are important. And it turns out we're learning that the cilia are not just mechanical. They actually have immune properties too. So even the cilia have specific immune properties that help in the battle against infection. The question is, does damage continue even though you stop? And in general, if you stop smoking, the destruction slows down and stops, okay? And that's true for a lot of the problems that you have with the lungs with smoking. If you stop smoking, you do have you have an increased risk of lung cancer if you smoke, but when you stop, as time passes, that risk of developing lung cancer decreases over time. Do you grow new cilia? I don't think so. You can correct me if I'm wrong, but I don't think so. So next, we talked about all of that was innate immunity, things that happen right up front. Let's talk very briefly about acquired immunity. And with acquired immunity, this really is the subsequent responses, which are more specific. So it's not just recognizing a uniform, but knowing exactly who your enemy is. Okay? Let's go back to those cells that we looked at before. And what you saw a few minutes ago was a neutrophil in that video that consumed Staph aureus, was that particular organism. Macrophages also can consume them. And actually, the myeloid line is also what produces erythrocytes, which are red blood cells. Not talking about those tonight. Now let's talk about the innate immune system, and that really focuses on lymphocytes, and specifically tonight, very brief words about T and B lymphocytes. So we've got a couple more vocabulary words, and those are antigen and antibody, okay? So when I'm talking about a specific immune response, this is a really specific response. So an antigen is a substance either within or outside the body that triggers an immune response, and in particular causes the production of antibodies, okay? So this is going to seem a little circular. What is an antibody? An antibody is a protein. It's also called an immunoglobulin. So if you've heard the term immunoglobulin, that's another word for antibody. This is produced by B lymphocytes in response to very specific triggers, foreign substances, or sometimes you might be familiar with the term autoimmune disease. Sometimes we actually make antibodies against ourselves. that's when you have failure of tolerance. Remember we talked about tolerance? You should be able to recognize yourself and not attack yourself. But for reasons that we don't yet fully understand, sometimes our immune system attacks ourselves and we can have problems with autoimmune disease. Thyroid problems, multiple sclerosis, lupus, those are all examples of autoimmune disease. So let's talk about antibodies which are able to identify and we'll say neutralize their target. Okay? So antibodies are very important. And one of the important things about antibodies is that by the time you're in middle life, how many antibodies, specific antibodies, do you think you might have? There have been estimates about this. So think about how many things your immune system has responded to. Remember when I said it works every second of your life? That your immune system has responded to and said, I need to make an antibody against this to protect the body. We're estimating probably 10 to the 9th or 10 to the 10th, billions and billions of specific responses and antibodies, and we can respond to them that precisely. So in this slide, an antigen, which let's say influenza, okay? You're exposed to influenza, or maybe there might be a better example if we're talking about an organism that gets consumed into an antigen-presenting cell, which is like the neutrophil or the macrophage. So probably better to take a different organism, but for that example, the organism is consumed, processed, and then presented to one of those T lymphocytes. And that T lymphocyte, one of the generals of the immune system, then makes decisions about how to respond to it depending on what kind of organism it is. So that lymphocyte can make a decision. Do I need to respond this way? Do I need to respond this way, or what? And that depends on whether it's a virus, bacteria, or whatever different kind of organism it might be. That decision is made. In the end analysis, and what we're going to be looking at tonight with Elizabeth, is the production, the communication to B cells to please produce antibodies specifically against this organism. And so the B cell then matures, and the B cell then ends up producing antibodies specific for that exact bug. Okay? It's a pretty cool system. So what does an antibody look like? Well, obviously it doesn't look exactly like this, but the point here is that this business end of this whole antibody is completely specific for only one organism. So if it's influenza, there is the influenza antigen, and here's an antibody that on the business end of this organism will only react to influenza. It's that specific, okay? It's just amazing. And I have a picture here for you, a close-up picture of a lymphocyte, and again, you can tell that this guy means business. Okay? This is not some flat beach ball sitting on the side with a nice cocktail enjoying the day. These lymphocytes are busy and active all the time. So this is what a lymphocyte looks like close up, and all of this part of the lymphocyte is very immunologically active. This lymphocyte would attach to a different cell, and when those cells talk to each other, the immune response occurs. Let me show you that right here again. So what happens is, let's say you've got a T cell here, the T lymphocyte, and it might have, this is obviously very bald here, it might have a lot of these things on the surface of it, but it has to go right up to that B cell, and we actually can get videos of it. I don't have one for you tonight, but they actually come right up to each other and they talk to each other, and then they kind of communicate and connect, and they have things that actually connect to each other to send signals. Yes? Yes, so here's the lymphocyte, the one that says T, thank you for asking, is a T lymphocyte, and the one that says B is a B lymphocyte. T is a lymphocyte type of helper cell, which is sending signals for another immune reaction. And here, this lymphocyte is developing killer T cells, another type of lymphocyte that works yet differently. So thank you for asking that and letting me clarify that. So these are lymphocytes that mature and have very specific reactions depending on the organism. That's how they make the decision. This was the blood cells, and here you can see a lymphocyte in the blood. Here's a red blood cell, and you can see how it's kind of shaped like a donut. It's very flexible, and that allows it to go into really narrow capillaries, even into the skin, so it's very flexible and bendable. And there are other cells in the blood also, some platelets that are kind of sticky and they allow for proper clotting. But this is just an example of how busy it can be in the blood with all different kinds of cells and activity. Okay, so we're just about done. So in summary, the lymphocytes, after they identify more specifically what the invader is, the lymphocytes then generate a specific immunologic response that specifically and maximally targets the pathogen. Okay? So lymphocytes are very important to orchestrate a very specific immune response. So they're really important. So did anybody get an influenza vaccine this year? Yeah, so probably most of you had a flu vaccine this year. And so guess what's happening when you get a flu vaccine? With the flu vaccine, where do you get it? Usually in the arm, right under the skin. So what happens when the immune system sees that vaccine that gets injected? There are sentinel cells, right? We've talked about sentinel cells that say, ooh, danger, this looks like influenza, even though it's not. It fakes the immune system out. And those danger signals send a message, eventually gets to the lymphocytes, usually in the lymph nodes, but can be other places. The lymphocytes then send the signal to produce ultimately those antibodies through the B lymphocytes. And so the next time you are actually exposed to influenza, what happens? Your immune system doesn't have to wait 4, 5, or 6 days to make that response from the beginning. Your immune system is primed. You've already prepared antibodies that are specific for that kind of influenza. So you're ready to go. Okay? So that's an example of how the immune system can respond with a vaccine. All right. So it's time to meet our patient. Why do we need to take vaccines every year? That's a great question. For the influenza, and the reason for that is that every year scientists around the world look to see which strains of influenza are circulating. Because some years there are many different kinds of influenza, and some years some are circulating and some are not. And so they make an educated guess based upon what they see in other parts of the world as to which types of influenza they think will be showing up in the United States each year. Sometimes they're really right, and sometimes there are new strains of influenza that come along. So if we're lucky, and this year we were pretty lucky, the vaccine was pretty much on target for the type of flu that came around this year. But that's a great question because it reflects the fact that there are many different kinds of influenza. But how many times in your life do you get a measles vaccine? Not very often. And your immune system has long-term memory. After you get that vaccine, it can remember it a long time. But influenza, there are different strains that look a little different every year. Okay? Let's move on and have Elizabeth come on up. I'm going to have Elizabeth stand right here, and I'm going to take a place right behind the podium. And Elizabeth is a patient of mine in clinic, and she's just a beautiful, delightful young woman who is such a pleasure to work with her. And she has a condition called common variable immunodeficiency, which is a horrible name, but it is a deficiency of immunity that has some specific manifestations. And I thought it might be helpful to the audience and helpful to me to learn more about Elizabeth by asking her a few questions. And so Elizabeth you were diagnosed with this immune deficiency at what age?
I was 7.
You were age 7.
Mm-hmm.
Okay, and what did you first notice? What do you remember about that time?
Well, and this is kind of from what my mother told me as well, because I was born healthy, no problems. I had normal vaccinations. About the time that I was 3 years old, I started to get really sick. I would actually go from specialist to specialist. One doctor suggested we take out part of my lung. I had my tonsils removed. I had my adenoids removed. I had tubes in my ears. I had ear infection after ear infection, cough, like just horrible coughs. It wasn't until I was about 7 years old that I went to Children's Hospital in Dallas, Texas, where I was finally diagnosed with common variable immunodeficiency.
Okay, and so were you missing a lot of school at that time?
I don't really remember. I don't think I did, but if I may have. I just always remember I was home. I remember the summer before I was diagnosed, I got really, really sick, and I had to stay home from camp. So I was really upset about that. But no, I mean, I functioned like a regular kid. I just was sick, but it was a sickness that was unexplained.
Okay. And so what kind of infections, you mentioned that you had ear tubes, so you were having problems with ear infections?
I had a lot of ear infections, very painful ear infections. I do remember that. I would be crying. My mom, she's like, oh my gosh, I cannot help you. I don't know what's wrong. Lots of ear infections, lots of throat problems. I was just always sick. Was really I mean, this is kind of going into family stuff, but my dad had leukemia, and at the same time, I was actually seeing the same doctors he was seeing, because they still didn't know what was wrong with me. So
Yeah.
that was a problem.
And so, so you had, sorry, go ahead. Yeah, so I'm going to repeat, yeah, and just to let you know, I'm repeating your questions because this is on videotape and they can't hear you, but the question is related to lab tests. Are there lab tests that can be done to detect this? And the answer is yes. But one of the challenges is that most doctors have not had training in this area. There aren't that many people who specialize in clinical immunology or problems with the immune system. And so most doctors either don't recognize it or they don't know what to do about it. But when you do suspect the diagnosis, there are some specific tests that you can order. And one of them gets right to the heart of what this gentleman in front was asking about, and that was the antibodies. We can measure the level of the antibodies, or lack thereof, in Elizabeth's immune system. And I think that's probably what they did at that time, because we were able to measure antibody levels. And with this particular condition, people with CVID may make antibodies, but they may be really low. And some people make almost no antibodies, whether it's IgA, IgG, IgM, or any of the different kinds of antibodies. So yes, that would be the first place to start, would be to measure the total antibody levels. And then there's some other tests that can be done as well, looking at a functional response. So remember how we talked about the vaccine, say an influenza vaccine, and you can be vaccinated and you get an immune response that helps you for the winter? We can actually use vaccinations like influenza vaccine, or say the pneumonia vaccine, which some of you probably had, called Pneumovax. If you've not had that before, we can measure your antibodies specific to pneumococcus, pneumococcal pneumonia. And then if they're too low, inappropriately low, we can give you the vaccine, and then 3 to 4 weeks later, we can measure it again, and we expect a certain response. We expect performance out of the immune system, and we can measure that. And so probably what happened with Elizabeth at that time was that she finally ran into somebody who said, whoa, she's having way too many infections. This is different than other kids. What's wrong here? Let's check her antibody levels. And what happened?
So a normal is between 800 and 1200.
For the IgG?
For the IgG, mine was 40. So they knew right off the bat that I was really sick. Mm-hmm. And they gave me the treatment, which is IVIG, and I have had that ever since 1990. And for now, I'm supposed to get it once a month for the rest of my life.
So what is intravenous immunoglobulin, IVIG? Remember how I told you that another name for an antibody is immunoglobulin? So we can actually, if Elizabeth doesn't make IgG antibodies, and she said her level was 40, which means pretty much that her immune system is not making antibodies. In our lab system, a normal range for level of antibodies in the specific quantity that we look at would be somewhere between about 650 and 1500, somewhere in that ballpark. And when she was first measured, she had essentially unmeasurable antibodies. Now there's another antibody that Elizabeth doesn't make either. As I recall, you don't make much in the way of IgA antibodies. And remember I told you that those IgA antibodies are in the gut, and they're very important for processing immune function in the gut. Okay? So now she's not making IgG. IgG is very important for respiratory infections. IgA, which is in the gut, you can start to imagine some of the problems that people have when they don't have these antibodies. So Elizabeth received the treatment of IgG infusions. We can give people infusions of IgG antibodies, and that's called intravenous immunoglobulin. It is possible to get it as an injection under the skin. If you get it by the vein, you get it usually once a month, sometimes every 3 weeks, depending on how fast your body breaks down antibodies normally. But sometimes, for reasons that I won't go into tonight, you can actually get it under the skin, but if you do it that way, you have to get it once a week. So there are different ways that you can receive these infusions of antibodies, and that's what Elizabeth has been doing for that time. So once you started on the intravenous immunoglobulin, did things change, and if so, how?
Well, tremendously. Something that I forgot to mention was that my doctors would prescribe medicines, everything from Augmentin, just any antibiotic under the sun. And for a 5-year-old to take a horse pill is very daunting. And the doctors would yell at my mother and tell her, "Your daughter is not taking her medicine. This is awful. If you don't give it to her, she's going to get sicker." My mother gave me the medicine. I took it. They didn't realize what was wrong. Since I've received IVIG, if I take any sort of antibiotic, anything of that nature, I can feel 10 times, 50 times better than what I initially went through as a child. So it definitely does help out a lot, and it's made my lifestyle a lot easier to take in. So.
But she still has to deal with receiving these infusions once a month. And of course, you know, she kind of has to plan her life around that. But Elizabeth is not to be deterred. Elizabeth is applying for nursing school. She's an A student, and she finds out next month.
Yeah, mid-March.
And the schools you've applied to are?
University of San Diego, Loyola, and Union University in Tennessee. So just obscure.
All right, so I can hardly wait to find out where Elizabeth's going to nursing school. Tell us what it's like to get the infusion. What happens when you go to get an infusion?
So I usually have to set aside 2 hours of a day. What's recently happened is that I have a nurse come to my house, so that makes it a lot easier for me because I don't have to plan my day around going to the hospital. He sticks me in, I sit there, I get my medicine. I have had some bad reactions to IVIG, but those are few and far between, and because I get it all the time, I don't really get that sick. I get a little run down, but obviously your immune system's just kind of kick-starting, so you're not always going to feel that great after your treatment, but always after the next day, I'm back to normal, working. I don't miss work for being sick. I don't miss work for going to get my treatment. I just consider it just part of what I have to deal with. So it's just one of those things that I go and do.
So the term common variable immunodeficiency really is a term that was given to this condition a long time ago because we didn't really know what caused it. And we'll talk about some of the genetic underlying causes later on, but it can manifest itself in a variety of different ways. But for Elizabeth, it's been predominantly these respiratory infections. So she had to deal with infection of the sinuses, infection with pneumonia, and different types of infection of the ear, really respiratory infections. And so tell us, has anybody else in your family had this condition or been diagnosed with it?
No one. They do think that my problem is genetic, and the closest that they found is just my father, who had been diagnosed with leukemia, but still no one in my family has what I have. So that was also something to kind of deal with because we didn't have somebody to work off of. So at this point, so far it's just me.
Yes, a question. Okay, great question. The question is, for each type of antibody, do you give a different infusion? And the answer is no. What happens is, you know how people donate blood at the blood bank? And some people donate in a different kind of process where the blood bank can actually selectively take antibodies out of those blood donations. They take the antibodies out, and Elizabeth, when she gets an infusion, actually gets an infusion of donated antibodies from a lot of different people, okay? So Elizabeth is getting the benefit of many different people's immune systems, and that's really nice. If you could take the immune systems of a whole bunch of people and be protected by that, her antibody repertoire, if you will, is much broader than mine because she's getting antibodies from a lot of other people infused into her. So this is a blood product, but thanks to the donors who are willing to do it, she's able to receive these different types of antibodies, but it reflects the entire repertoire of very specific antibodies, whatever that individual has circulating around. So they get a lot of antibodies of all different kinds. Yes, so the question is about autoimmune disease. And autoimmune disease can occur in patients with common variable immunodeficiency, but not as a consequence of receiving other people's antibodies. It can be one of the manifestations of this particular disease. And so we'll talk about that in just a minute when we go back and look at the exact part of the immune system that's involved with her disorder. But no, receiving the antibodies, which is a very interesting and good thought, receiving the antibodies of others is not associated with her having a higher chance of developing autoimmune disease. We're actually looking at whether or not maybe she would be less likely to get it. So we're following a lot of patients over time to see if it might be associated with a decreased incidence. But of course, that's hard to do because I don't have a placebo patient. I'm not going to tell some patient with CVID, sorry, I need to compare you to Elizabeth, so I'm not giving you immunoglobulin. We can't do that. But these are all great questions. So there's a question in the back. I apologize, the light's a little bright. Yes, sir.
Well, my sister wasn't either. My sister was not either, and she doesn't have what I have. So.
And that's a great question. You do get a whole host of antibodies from the mom when you're in the womb. So the first 6 to 8 months of our lives, our immune systems are not mature enough to actually produce the antibodies. So we receive antibodies from our mothers through the placenta. And those antibodies will protect us for the first 6 to 8 months or so of our lives, those IgG antibodies from mom. But those finally wear off as our own immune systems kick in. In general, the breastfeeding is probably not going to be associated with the development of this kind of immune deficiency, but you are correct that it probably is associated with some types of problems with the immune system and maybe even with certain types of hypersensitivity of the immune system, maybe some types of allergies. So that's another area of research. Yes, ma'am. So if a healthy person were to receive an infusion of immunoglobulin,